Um, we are now going to move into the Geotechnical Properties session, session 3, and we have Luis Torres again online speaking to us on drained and undrained shearing conditions. It's about 1 o'clock in the morning, if I get that right for Luis, so hope he's had a few cups of coffee. But anyway, welcome back. Luis, are you online and ready to present?
I am, Andrew.
Okay, go ahead and share your slides, and all over to you.
Thank you. Okay, you should all be able to see my slide right now. Please let me know if you cannot. And this should be a relatively short presentation that is based on Appendix A of the bulletin, and more specifically section A 2.1, and which deals with drained and undrained shearing conditions. So there are a number of key concepts that I would like to address in discussing this topic. So let's go through them. So firstly, this presentation is going to assume that we are dealing with saturated soils and that therefore the principle of effective stress is applicable. Secondly, we have to keep in mind that pore water pressure in any granular medium has two components, or at least the pore water pressure can be thought of as having two components. One is the ambient induced pore water pressure, which we generally label U0, and the other one is the shear induced pore water pressure, or excess pore water pressure, which we refer to as UE. So the pore water pressure of the soil is the addition of those two components, the ambient induced and the excess pore water pressure. So this ambient induced pore water pressure is determined by the seepage regime of the soil, or lack thereof, because you could also have a hydrostatic regime, and this has absolutely nothing to do with the soil density. So for instance, if we consider a hydrostatic scenario, and we assume that the water table is at ground level, and we want to know what is the pore water pressure, let's say 2 meters below ground level, which coincides with the water table, then we would say that U0 is equal to those 2 meters times the unit weight of water. And that's it. That's where our considerations stop. We don't have to worry about whether it is a sand or a clay, or whether the soil is dense or loose. That U0 is totally unrelated to those considerations. Now, on the other hand, we have the excess pore water pressure, UE, which arises because soils have a tendency to change the volume of their voids. In other words, to change the volume of the space in between the particles when they are sheared. And more specifically, when loose soils are sheared, they tend to contract. And when dense soils are sheared, they tend to dilate. In other words, to increase the volume of those voids in between the particles. Now, notice that in point 4 above, I have said that soils have a tendency to change the volume. They will not necessarily change their volume, and that's what I am addressing in point 6. That is, soils may or may not fulfill their volume changing tendencies. So in point 7, we are defining what is a drained condition. A drained condition is one in which zero excess pore water pressure develops. No excess pore water pressure whatsoever develops. Why not? Well, because water is free to move into or out of the voids of the soil. In other words, water is allowed to be squeezed out of contractive soils, or it can be sucked into the voids of dilative soils. Under undrained conditions, in the other hand, we have zero dissipation of the excess pore water pressure. So under drain conditions, we have zero development of excess pore water pressure. And under undrained conditions, we have zero dissipation of the excess pore water pressure because water cannot exit or enter the voids. So we're having here a condition in which generally the excess pore water pressure is not zero. Now, I'm gonna come back to the point of why water may not be able to exit or enter the voids just now. But before I address that, let me point out that generation of excess pore water pressure is critical to the stability because through the principle of effective stress, which is applicable to saturated soils, that pore water pressure is going to have an effect on the effective stress, and in turn that effective stress is going to have an effect on the shear strength. So a high pore water pressure, by virtue of this negative sign right here, a high pore water pressure means a low effective stress, and that low effective stress will imply a low shear strength. Now, in contractive, or in other words, loose soils, the excess pore water pressure is going to be positive, right? So you're going to have a large pore water pressure, and that is going to result in a drop in sigma prime, and therefore a drop in tau, and that is not good for stability. On the other hand, in dilative or dense soils, the excess pore water pressure will be negative. So that negative UE with this negative sign over here results in an increase in effective stress, and therefore also an increase in shear strength, which is good for dam stability. The implication of that is that in contractive soils, undrained behavior is going to control stability, whereas in dilatant soils, drained behavior will be the scenario that controls stability. Now, let's go back to that question of when do undrained conditions arise? In other words, under what conditions is water unable to be squeezed out of the voids of contractive soils or sucked into the voids of dilatant soils? So let's start with perhaps the simple scenario, which is what happens in the lab. So here I am showing you that that picture again of a triaxial test specimen mounted on the base of a triaxial cell. And what I am highlighting here is that these cells are fitted with valves, right? And these are the valves that allow water to flow into or out of the specimen. So in the laboratory, if one wants to enforce undrained conditions, well, it's really very simple. All I have to do is close this valve and done. I have an undrained specimen. On the other hand, if I want to enable drained conditions, then I leave the valve open so that water can flow into and out of the specimen. Now notice, by the way, what I have said here, that opening the valve enables drained conditions, but it does not guarantee them. Because remember the definition of a drain condition, the definition is not that water can move in or out of the specimen. The definition is that no excess pore water pressure will develop. So opening the valve by itself does not guarantee that pore water pressure, or that excess rather, pore water pressure will not develop, because you still have to load the specimen slow enough to make sure that that excess pore water pressure does not develop. And this is the reason why, even when we are doing drained triaxial tests, and we are not expecting or we are hoping that there will not be a development of excess pore water pressure, we still measure the pore water pressure to ensure that indeed that excess pore water pressure is equal to 0. Now, generally in the lab, we run these triaxial tests in what is known as a strain control test or deformation control test, in which we are controlling the rate at which the specimen deforms. And that allows us to control whether that loading is quick or slow enough to prevent the development of excess pore water pressure. Now, that is not the way soils are loaded in nature, right? In nature, well, or in reality, in an actual TSF, it is stress that is controlling the loading sequence. And as we can see in this, this is a result of a stress controlled test. And we can see here that loading, when it is stress controlled, can actually occur very, very quickly, and that can lead to the development of undrained conditions. So we've looked at the case of undrained conditions in the lab. So let us now consider, when do undrained conditions arise in the field? So strictly speaking, this would be the same as asking, when is there no dissipation whatsoever of the excess pore water pressure in the field? And the answer that I am suggesting here is probably never, right? Because in the field, there is no such valve that you can open or close. So there is always likely to be some degree of dissipation. We can never guarantee that there is absolutely zero dissipation of excess pore water pressure in the field. However, if the volume changes that are occurring in the field are happening quickly and the drainage paths are long, then even sands and non-plastic silts can generate significant amounts of excess pore water pressure. And we refer to that condition as an undrained condition, even though it is not, strictly speaking, a perfectly undrained condition. So the key consideration here is that in the field, you can have circumstances when the excess pore water pressure will be generated at a much faster rate than it can be dissipated. And so that is what we refer to as an undrained condition. Please notice then that whether a soil is drained, or rather whether it is exhibiting drained or undrained behavior, is precisely that. It is a behavior. It is not a soil property. It is something that is emerging from the velocity, from the speed at which these volume changes of the voids are occurring. So there is no such thing as a drained soil or an undrained soil. It's just that a soil can behave in a drained way, or it could also behave in an undrained way. I want to point out these charts that I made reference to earlier. So these are, I will recall here, based on CPT results, and they are divided into drained and undrained areas and also areas of partial drainage. So I just want to clarify that when something falls here, let's say on the drained area, again, it doesn't mean that the soil is drained or that it will always exhibit drain behavior. It simply means that during the cone penetration test, it exhibited drain behavior. And same thing over here. If your data is plotting in this area, if your results are plotting in this area, it means that during the cone penetration test, the conditions were undrained. Okay, so this is what happened during the CPT. It is not the expected behavior of the TSF. And lastly, I want to point out that, well, of course, this excess pore water pressure has to be accounted for when calculating tau because of these two equations that I showed earlier. In other words, that development of excess pore water pressure has an effect on effective stresses and also on shear strength. So one possible approach would be for us to attempt to predict the excess pore water pressure, recalculate sigma prime, and recalculate tau accordingly. But much more commonly, what we attempt to do is what Andy alluded to already, is that we try to estimate what is the value of this shear strength ratio. So the undrained strength divided by the vertical effective stress. And here we typically distinguish between two types of undrained strength. One would be the peak value shown over here in the graph, and the other one would be the residual strength. And well, my colleagues already discussed how one may go about estimating the values of these ratios. Right, so my closing remarks, the volume change tendencies of soils lead to the development of excess pore water pressure when water cannot easily move into the voids or out of the voids. And this excess pore water pressure has a direct effect on soil strength that has to be accounted for in stability analysis. Thank you for your attention.
Are able to stay with us, that's great, but we would understand if you did leave us and took some time to get some sleep. We're going to move on then to the next presentation, and there's two in a row here from Andy, but the first one is dilative versus contractive behavior, to be followed after that by CPTu-based measurement of state. Back to you.
Sandra. Yep, me again. Could I go out on a limb here and say that maybe as we're going through this session, if you have particular questions that maybe you want to clarify something, you put up your hands. I'll try and see you with the spotlights, the searchlights on me, but rather than waiting until the end, maybe. So if there's something burning, or if you think you want to clarify, because we've got a little bit of time, I think we're about 5-10 minutes ahead, so maybe some discussion while we're going could be good. Who knows? All right. So going into here, so it does build on what Louise has just been talking about. I also wanted to make an acknowledgement here. So quite a lot of the slides I've used in these various presentations were from the workshops that David Reed and myself ran, as I said, probably starting 7 years ago. So he made my life a lot easier for this particular workshop by having produced many of the slides, which I've drawn on and maybe modified and so on. So David made a huge contribution. All right, so going to kind of tackle this, I guess, from a different point of view to kind of lead into why this transition to undrained shearing is so critical and what's different about it, etc., etc. Now, Steve Vick, who's published some really, really insightful work over the years, he suggested thinking about loading, and it's very applicable to tailings facilities, using 3 kind of separate loading scenarios. Now, as with many things, they don't occur in isolation necessarily, but they may, just because I'm from Australia doesn't mean you have to supply the flyers. It's just you've got these 3 scenarios which kind of have decoupled here, but they could be occurring simultaneously. But let's look at them. So, in terms of the first one, how do we increase pore pressures? The 3 mechanisms. The one is pretty obvious. You've got an element of tailings there, the black square below the phreatic surface. And as the phreatic surface rises, the total stress is maybe changing a small amount, but the pore pressure is increasing very significantly. When you look at triggering mechanisms tomorrow, you'll see that this results in a stress path which pushes you towards the stress conditions under which you can actually trigger this transition to undrained shearing. And we'll elaborate on that a bit more tomorrow when you talk about triggering. So that's mechanism 1. Now, maybe that's in isolation. The second one is the one, again, we're kind of familiar with. We maybe think about when we think about rate of rise calculations in TSFs. That's where we're applying essentially a vertical stress, an increase in vertical stress. So that element of tailings, it's still the same depth below the phreatic surface. The phreatic surface probably not responding to the load, but there's this rapid increase in total stress, which the element of tailings maybe reciprocates by an increase in pore pressure, which therefore affects your effective stress and hence your strength. Now, this is something we probably sometimes use perhaps just implicitly, the B-bar approach, where you say, okay, I'm going to imagine I've got a B-bar value of 0.8, which means your pore pressure response is 80% of the total stress that's applied, and you look at how that affects stability. And people, I guess, are familiar with that. Doesn't have to be a slope, however. I mean, you can get this in a horizontal ground as well. But you get this zone of excess pore pressure due to the vertical load. Now that's, again, the term high rate, it's all relative, as in many things when you're talking about sort of soils or tailings. The rate of load is high enough that it doesn't allow dissipation of pore pressure during the application of the load, which is obviously a function of how quick you're building, but also the permeability of that material that's being loaded. So if you've got a really coarse, gravelly type material, you can load it a lot faster than a silty tailings without generating excess pore pressures. It could also be, as I said, just horizontal ground conditions. So it's not really anything exclusive to tailings. But it's really the third mechanism that Vic identified, and probably didn't explore in great detail because he wasn't thinking only of kind of very loose, cohesionless materials. But that's this contractive undrained response. Louis has kind of dealt with undrained in some detail, which then causes in itself an increase in pore pressures, excess pore pressures. So, and this is like analogous to the phenomenon that we've now come to know as static liquefaction. It does go under other titles, but it's liquefaction in the absence of dynamic stresses, in the absence of an earthquake, in the absence of any kind of cyclic loading, which was kind of anathema to a lot of people initially, I think, is that, again, you think about undergraduate soil mechanics, sands behave in a drained fashion, they never experience undrained loading except in an earthquake. And that was kind of like that little caveat that we all kind of got to know and accept, because the evidence showed that that was the case. But how can we transition to rapid undrained shearing in the absence of cyclic loading? And again, it has very little to do with the permeability itself. It's not as though you can not get this phenomenon if you have a high enough permeability, because it's the balance between the rate of application and the rate of dissipation. Remember that. So again, come back to that one slide I mentioned today. You can have a CPT, which is at a rate that puts you in a drained CPT, on the left of that normalized velocity curve, but that doesn't mean it cannot behave in a contractive fashion, just because the CPT was drained. So, in terms of thinking about this, what matters, what's key for this mechanism 3, and whether it develops or not, is the soil loose or is it dense? And of course, again, we have to have something to tie it back to, something that's a relative measure of density. So maybe we need to step back a bit and talk about the determination of critical state line again. You've seen it a few times today, but it's probably not a bad thing. Again, I make this point: I think through necessity and through the need to try and clarify what is a really difficult subject. At undergraduate soil mechanics, we distinguish between sands and clays, drained and undrained. And kind of implicit to a lot of that training is that we've got kind of a unique relationship between density and stress, some measure of stress. So that vertical axis is density or void ratio, just kind of the inverse. And if you think about it in a tailings storage facility, on the beach, each time you place a new layer, it's a very low total stress. So it's in that very low stress range, pretty high void ratio. Maybe you get some bleed water, which means the void ratio decreases initially, but then it has to decrease further, either through additional loading, through drainage, the loss of water, that's probably a small component, or you can get this desiccation effect due to the drying effect of the sun. That's like applying an additional effect of stress, which drives you further down that diagonal line that I've shown there. But the key thing on this slide is that undergraduate soil mechanics, we assume that there's this unique relationship between density and applied stress. And again, you stop at some point, you unload, the void ratio changes marginally. You might get a little bit of rebound, maybe a slight increase in void ratio. But compared to the amount of compression, the amount of void ratio change that occurred on that black line, it's really insignificant. So again, that's consistent with what you learned when you look at odometer tests and interpretation of odometer tests in undergraduate soil mechanics. Now, it might be often the case for clay-type soils, but I think, as we've already alluded to, is that with many cohesionless tailings, silty, sandy tailings again, there's quite a range of consolidation lines that might be applicable. And sometimes they converge, but very often they don't all converge on a unique, one-dimensional consolidation line. So we talk about it as the perhaps accessible densities. And what governs that difference, I guess, is your starting void ratio. So it's that initial void ratio at low effective stresses. So you kind of start higher up, you remain higher up, compared to perhaps a tailings that's placed at a lower void ratio. So one of the examples that's often quoted is from Jeffries and Bean, from this oak sack sand. So that myriad of lines you see there, the thinner lines, are a range of consolidation tests on samples that were either prepared using the moist tamping technique or some kind of pluviation method. And this is maybe an extreme example, but as they were loaded up, they kind of kept their distance from one another. They didn't converge onto a single, unique, normal consolidation line. And this is what's often referred to as transitional soils. I guess the term just came up because it's not really sand, it's not really clay. And there's ways to determine kind of almost the degree of transition. So if those normal consolidation lines converge at moderate effective stresses, that might be a different designation than if they converge at extremely high effective stresses. But sometimes those stresses might be kind of equivalent to a 400 meter high TSF in terms of the stress required. So for a lot of tailing storage facilities, maybe 50 meters high and less, or even perhaps a bit higher than that, they're in that range where the convergence doesn't always happen. So you've got these unique normal consolidation lines. And some data dug out of the forensic report from Morgenstern, where they'd been consolidating from different initial stresses. These are the points at which they started shearing. But you can see they're kind of lying either side of the critical state line for that material. So when I talked about Shansep prior to lunch, that was on the supposition that your normal consolidation line, your critical state line, stay parallel and stay the same distance apart. And whereas here, they can be either above or below. So you get this range of kind of accessible densities, depending on where you start, and potential convergence at higher stresses. But it doesn't appear to be always the case. But just to emphasize that range that we're looking at there, below 1,000 kilopascals, that's applicable to many, many TSFs around the world. So it's not as though it's kind of outside the range of interest by any means. So now, thinking about that kind of limitation or that undesirable behavior, we come to this concept of what is loose and what is dense, and how do we differentiate that. So in this space that you've now seen a number of times, void ratio against mean effective stress, that's just the average effective stress, sigma 1 dash plus sigma 3 dash plus sigma 2 dash over 3. That red line represents this critical state line, and it designates material that's loose in that kind of that green box and dense below it. Now the reason we've drawn that green box as sitting below the critical state line is that when you look at a lot of the kind of recommendations on what constitutes contractive behavior, people talk about minus 0.05. In other words, below the critical state line. It's in that little region between the bottom of that box and the critical state line. So it's not saying it's only above the CSL, but I guess based to some extent on back analysis of failures and maybe some inherent conservatism, the actual boundary is taken as parallel to the critical state line, but offset by minus 0.05. Now, Lewis mentioned the round robin study we did a couple of years back at UWA. He mentioned that this morning and said that even with really pretty reputable laboratories, we had a range of void ratios of 0.1. You might recall that. It actually wasn't as bad as that. That's the good news, is once we filtered out some tests which were done with very strange, perhaps, approaches, etc., and we took out the samples or the laboratories that kind of followed Jeffries and Bean's approach in the Appendix B of their book, including use of end-of-test freezing, which frankly we far prefer than any other technique. I don't see any reason not to use it. It's very simple. We've never had damage to the platens, and it becomes such a routine. All our PhD students use that technique and get very reproducible results. So with that, we got onto a band of about 0.04 as the kind of scatter, if you like. And that was about the top, I think, 8 or 9 laboratories. So 0.04, here we've got this kind of offset of minus 0.05. So maybe, even though it is probably unintentional, building in that extra kind of conservatism is probably a very good thing, because it's allowing for that inaccuracy of determining critical state line. Or maybe inaccuracy is the wrong term, but just a variability. Okay, so now we're in this, we can now start to distinguish between what's loose, what's dense. What do we mean by that? It's those, that differentiation based on the critical state line. And then again, just to emphasize that the state parameter is the offset from that critical state line. Now, if you're just above that critical state line, it means the potential change in volume on shearing is actually quite small. You know? So imagine you trigger undrained failure. It wants to go to critical state. It doesn't need to undergo much void ratio change. Whereas if you're way above, like the top of that box, you've got a very large state parameter. So the potential change in void ratio, i.e. volume, is extremely large. And I think therefore the generation of excess pore pressure is more pronounced the further away you are from the critical state line. So when we're thinking about, again, what happens when we trigger this undrained shearing, I think the behaviour post that is, again, largely determined by how far you are offset from that line. And I think that's something that probably hasn't been explored sufficiently. Now, if you look at the Brumadinho video, and I don't know how many of you have lost sleep over after watching that. I know I certainly did. Yeah, I just thought that we have no idea what we're doing. But if you watch how that failure propagated, you had that initial event near the bottom of the slope, and then within seconds, you had the slumping and the kind of failure propagating to the top of the slope. I think that material would have been at such a high state parameter that as you kind of tipped it over the edge, I've just lost. Okay. No? Okay. So I think as it kind of got tipped over the edge in terms of starting to generate those excess pore pressures, because it was so loose, those very large pore pressures that were generated propagated throughout the slope, because water is essentially incompressible. So if you generate a pore pressure, it can propagate at something like 600 meters per second, I believe. So it probably, to kind of personalize it a bit, it communicated with the tailings throughout that slope, which then kind of followed suit. And that's why you had that incredible kind of communication, I believe. Now, maybe if it hadn't been at quite such a high state parameter, it would have been much more localized, that generation of excess pore pressure, which is what the report from Barcelona suggests in terms of an incident that happened many months before the main failure, where they had a similar event, localized liquefaction, but it never propagated. So it's important to know whether we're above that contractive boundary, but I think it's also useful to know how far above it we are. And that's where, again, this whole challenge of undisturbed sampling comes in. So, again, just in summary, positive state parameter is where you don't want to be. That's the bad news. Now, step back again, maybe some simplistic explanations of how density affects shearing. So you've got a couple of sketches there. The one on the left is physically impossible. Top left, because the particles are not in contact. But remember, it's a three-dimensional structure, so perhaps they're in contact out of plane. But you've got really loose material. It's under some confining stress. When you start shearing it, the top right sketch pertains, particles become closer together. The volume tendency is to decrease. Okay? That's contractive behavior. Opposed to that is the bottom left, where it's packed probably as dense as it can be. Minimum void ratio, which is why we compact fills. Upon shearing, those particles cannot move horizontally relative to one another without pushing apart, without dilating. So that's all dilation is accommodating the applied shear stress through expansion, through allowing that increasing volume under the application of a shear stress. So if we have a true undrained test now, so we've closed that valve of Lewis and we're applying the shear stress. Remember, water cannot move across those boundaries. It's an undrained test. Those loose material is trying to compact, it's trying to decrease in volume. Cannot do that. So the pore pressure takes that additional compression. That tendency for a volume decrease is accounted for by an increase in the pore pressure. Sorry, I think I might have got ahead of myself there. I'm talking about a dense soil here, sorry. Just scrub what I've said the last minute. You've got this dense soil. Again, the water can't escape because the boundary is impermeable. Because it's trying to dilate, it's trying to expand, the pore pressure responds by going negative or relative to the starting condition. So you're getting this expansion, pore pressure can't move out of the element, so it responds by decreasing. Go to your effective stress equation, that drives the effective stress up. So as you're dilating, the effective stress is going up, so your shear strength is going up, and your stiffness as well, but the shear strength that we're essentially interested in. So the sort liquefaction is then impossible. Your pore pressure is going negative relative to the starting condition, and you're getting a higher undrained strength than you get a drained strength. Okay, this is what I was wrongly talking about the last slide. So here we've got a loose soil, undrained, again, water can't cross the boundary. It's tending to contract. The water resists that contraction. The pore pressure goes up. Pore pressure goes up, effective stress goes down, strength goes down as well. And if that's of sufficient magnitude, and you have undrained or near undrained conditions, then we get this phenomenon of static liquefaction. If that was occurring at a rate such that the pore pressure could be dissipating, then perhaps we can avoid the static liquefaction. And that's where, again, maybe when we've got loose but not terribly loose, maybe we can dissipate quickly enough. So, okay, a couple of important points then. If we trigger this transition, if we trigger this generation of excess pore pressure through shearing, through mechanism 3, the rate of that continual kind of feedback loop might be such that even a coarse sand, cannot dissipate in time. So even high permeability soils could be susceptible to this. It doesn't prevent contractive behavior of sandy tailings. And again, the loading can be drained right up until the point where this undrained shearing is triggered. So it doesn't require undrained application of load. You can be drained, it can push you further and further up in that stress path. Fourie was talking about a low K0 means you closer and closer to this instability region. That whole process could be drained, but it's putting the material into a state such that it's highly susceptible to triggering into this undrained behavior. And once that happens, it might be a complete runaway. Here in terms of very simple stress paths, we've got shear stress against mean stress or mean effective stress on the horizontal. When you do a triaxial test, we apply vertical stress, keep the horizontal stress constant. We have a stress path that is essentially 3-to-1 in that space. That's the total stress path. But depending on whether we're dilating or contracting, it goes one of either way. So the line on the right, it's dilating. We're generating negative excess pore pressures. So it's veering away to the right, and we get to that limiting stress condition, which in this case is the critical state condition, the MTC or phi-dashed, at a higher shear stress value than if you did a drain test. You tested the sample slow enough that you generated no excess pore pressures. You would hit that dashed line when the 1 in 3 slope intersects that line, which would be kind of somewhere between those other two lines shown there. Whereas the curve on the left, you're generating positive pore pressures, which is pushing you to the left in stress space. You reach that limiting condition, in this case, way before you would in a drain test. And this is even in the absence of super contractive behavior, when you actually get a limiting shear stress even before you get to that friction angle, as we'll see later. Just simplistically, on the right top, we've got that same kind of figure. Below that, you've got the plot in the space of density or void ratio against effective stress and your critical state line. You can see the curve that's starting above the critical state line moves to the left because you're generating positive excess pore pressures, hence you intersect the limiting stress state at a much lower value of shear stress than the other test, which is below the critical state line to start with. You generate negative excess pore pressures and you actually end up with a higher strength than even the drain strength. So again, we have this boundary, the solid black line, which is the minus 0.05. That's really, actually turns out to be quite similar to Robertson's QTN CS line equivalent to 70. That's on that plot of tip resistance against friction ratio. Louis showed this in a few forms today. And that value of Q equal to 70 has become very widely used in our industry. And it's not a bad option. I still way prefer trying to go the state parameter approach, but we have various techniques at our disposal, and you really should only discard them when we show them to be really implausible. So there's kind of a nice synergy there, I guess, between the QTN CS approach and the state parameter approach. But without being too dramatic, it's tailings that are in the state given by that green box that cause all the problems for us. Okay. Tying that now to some of the design parameters we start using. What actually controls these two strengths that we use all the time now, that ANCOLD, talk about ICOLD, GISTM, etc., etc. The peak strength and the post-peak, or the large strain. I don't like the term residual. Some people call it post-liquefaction, large strain, whatever. It's like, we know what a Hoover is, right? You know what job a Hoover does. It's a vacuum cleaner, right? So let's not get tied up in the semantics. I think we all know what we're talking about. It's that large strain strength. So what controls the magnitude of that and the residual post-peak large strain strength? What can trigger that undrained shearing process? And critically, how brittle is that drop from peak to large strain? And when people talk about brittle, they tend to focus on the difference between peak and large strain strengths. And I'll show the definition of Bishop shortly, the brittleness index. But to me, what is probably even more important, is the strain range over which that occurs. And again, I'll try and draw that out a bit later on. So here, Bishop said, let's talk about our brittleness index. I'm sorry, this is, I thought I'd got rid of this slide. This is a slide I put in from another presentation, so ignore that little red dot. So the brittleness index is the peak minus the residual over the peak. Okay, so let me go back a sec. So it would be that peak minus the residual over the peak value. So here, I've drawn a couple of sketches. Here we've got material, let's say material A, the solid line. Shear stress against axial strain. You've got a peak value, it drops to a post-peak. The dashed line is sample C. It goes to a peak and then goes to the same post-peak. They've got the same Bishop's brittleness index. Yeah, would you agree? Are they equally brittle? And I mean, you know, Bishop did this 50 years ago when he was doing the forensic investigation of the Aberfan failure in Wales. And you know, it was kind of quite insightful then. But I think as we getting into even more contractive materials, we need to go a step beyond this, just the Bishop's brittleness index, I think. And maybe we can have a debate about that tomorrow. And just to note that if that value is equal to 1, it means it's complete brittleness. That's complete failure. You've got no large strain strength. So it goes from 0 to 1. And the ICOLD bulletin has, you know, I think Appendix B, a diagram looking at kind of degrees of brittleness, depending on this kind of post-peak behavior. Okay, so that brings us back to the topic I kind of initiated, talking about what state governs your stress-strain behavior, both peak and post-peak. So there we've got 3 samples in the field at different in-situ state conditions, one just below the critical state line, perhaps in that region between the CSL and negative 0.05, one higher up, and then one way higher. Now, the one at the, if you put the 4th one in, very low value of state parameter, that's not going to cause any problems. That's going to be highly dilative. Probably highly unlikely as well on a hydraulically placed TSFs. Maybe some of these filtered stack TSFs that are being built, you might start in that condition, but just to be quite frank, you may not stay in that condition, but that's an entirely different debate. We're interested in those states that are higher up on that curve. State parameter values of 1, 2, and 3. Now, I guess, but superfluous, we've covered this, that, you know, need to be less than about negative 0.05 to ensure dilative response. But here there was, we prepared samples at those state parameters up to 0.096, let's say 0.1, which, if you look at some reports these days, that's a relatively low state parameter value. I'm seeing values of 0.2 and 0.25 and so on. That's sometimes hard to imagine. And I think it's just a very non-discerning interpretation of test data. It's very hard to make samples in the laboratory at these high state parameters. People who've worked with moist tamping know how difficult it can be. Is you get a loose sample, the minute you start saturating it, it just collapses. So, but these are plausible values, these are actual data. So the one that's just below the critical state line, and really just below, has a peak undrained strength ratio, around about 0.4. Then you get that decrease, and then you get this kind of quasi-steady state behavior people talk about, where it starts dilating eventually. So it doesn't follow that full contractive behavior. The 0.03, the middle line, it mobilizes a lower peak and it exhibits brittle behavior. Bishop's brittleness index there would be probably 0.95 or something. And then the very high state parameter, 0.1, mobilizes an even lower peak and even more dramatic loss in strength. Brittleness index of 1, but also complete liquefaction, essentially. So I guess the point here is that contractive is one thing, but then the way it manifests once perhaps liquefaction is triggered might be completely another. And again, Brumadinho was probably analogous to that green line, i.e. the one that mobilized the smallest peak and the most brittle post-peak. So are we above or below the critical state line? Question one. Probably how far above is really important to know as well. A couple of people have mentioned this instability stress ratio, so it's important we make sure everyone's on the same page here. On the right, we've got an undrained test. So remember, no volume change. We apply a total stress, but the effective stress does what it wants, depending on whether the sample is contracting or dilating. And in that case, we get the black line shown. It mobilizes a peak shear stress at a value that's lower than you'd get if you had a drain test. This is where you're triggering this undrained transition. So we reach that peak well below the line that's equivalent to the friction angle, or what's called MTC, the M value for triaxial compression. So this is why we carry out these strength ratio calculations, CE over sigma dashed. If the material is contractive, we really need to do these analyses, and we need to know what those numbers are to determine what we plug into the analyses of peak factor of safety. So that's governed by what's called this instability line, and that depends on void ratio again, and you can approach that instability line under drained loading and probably sit quite happily below that instability line, but a small perturbation can kind of push you towards it and over it. We've even shown Ricardo Fanny, who's just submitted his PhD using the hollow cylinder device, has actually taken tailings into a stress state above the instability line through very, very careful drain loading, but then a really small perturbation. You don't even see an increase in deviator stress. Failure is triggered. So it's like having a ball sitting at the top of a really curved hill. It's very, very stable, but the minute you touch it, instability. That's what above that instability line would mean. You're in the kind of twilight zone there. So here we've got state parameter for it's a couple of materials. We use the silica fine sand for a lot of our comparative work because it does show very brittle behavior. It's also something that the centrifuge people use a lot. It's like a standard testing material, but it behaves in a very nice brittle manner. But then there's also some tests from Fundão. That was the failure that happened in 2015 in Brazil. And it includes isotropically consolidated, anisotropically consolidated, and what we call the CSD, constant shear drained test. That's analogous to a phoretic surface rising, where you increasing the pore pressure, decreasing the mean stress until you hit the instability line. And you'll see that the higher the state parameter, the lower the instability ratio at which you trigger that failure. So again, how far away you are from that critical state line determines the peak strength that can get mobilized. So, talked a little bit about testing this morning. Clearly then, CPT testing, cone tip resistance on its own is not enough to tell us if it's loose or dense. For example, a loose sand, silty sand, might give you the same QT as a dense clay silt. So you need the pore pressures and the sleeve friction to interrogate that further. So don't lose sight of that. I think this is a really insightful figure. Kind of draws together a lot of the stuff I've been talking about here. I refer to Ken Bean. I saw him give this presentation at a conference on the Gold Coast, but I think other people may have done it before. So the left, we've got deviated stress, mean stress, the effective, stress path plot. Sample A has been isotropically consolidated up to a p dash of 200, as is sample B1, as is sample C, all same value of p dashed. Undrained loading, sample A starts contracting, you get to that peak Q, the instability line or instability locus, and you get strength loss. So if you look in the right curve, sample A goes up, hits a peak, starts essentially strain softening, losing strength. But it took a lot more displacement or strain to get to that peak, and it took a lot more strain to lose that strength. Look at sample B. It's sitting just below the instability locus. And again, SVO was talking about that this morning. Been taken there under drained loading, then a small application of shear stress. You can see in the right-hand curve, those two lines that are parallel. That's your reserve for that sample. That's the increment of shear stress that you can apply before you hit your instability line and trigger uncontrolled contraction, undrained shearing, and strength loss, as you can see on the right. And then the worst is you take it into the twilight zone, sample C, immediate loss on strength, on disturbance. And that Ricardo has shown this experimentally through a few different stress paths. So it's not a complete kind of fabrication of someone's imagination. This is true behavior. Again, I would speculate that Brumadinho was somewhere between sample B and C, probably. Needed a slight nudge to go over the edge and generate this kind of behavior. Something I've mentioned before, but let's just emphasize it. The cone tests at Fundão, through the sand, that was the higher tailings, those tests were drained. And yet that material failed in undrained shearing. So, in situ, that sand, it was drained, probably fully drained, throughout the TSF life until it wasn't drained, until contraction was triggered. The slimes or the fines below that sand, they were drained for the majority of the TSF life. It was built up slowly, pore pressures were probably dissipating, but when the critical condition was triggered, it transitioned to undrained. And that's when static liquefaction occurred at Fundão. And that was the findings of the Morgenstern forensic report. So again, determining what constitutes dense and loose, it's this laboratory testing critical state line. We've seen that a few times today. I want to mention a few things related to that. We use this moist tamping method. It's become widespread. There's various ways to make sure you get the same layers, etc., etc. I don't want to go into that because it's been dealt with elsewhere. There's still some controversy about moist tamping because people argue that it doesn't reproduce the in situ fabric of the tailings, where fabric is kind of particle arrangement or structure or something. But I think it's been mentioned before today, earlier, that your critical condition is relatively impervious to your method of sample preparation, except if you get segregation. And that's why we don't like the slurry deposition methods, because for many materials, you try and do a deposition underwater, the fine and coarse particles segregate. Then you're not testing a homogeneous sample. But let's just look at this for a minute. Bit of a diversion, but it doesn't matter. We do see differences depending on the method of sample preparation. That may be relevant to small strain behavior. But we would argue that no sample preparation method has yet kind of reproduced fabric. It's really hard to quantify in situ fabric in terms of how to actually put a number to it, or what to use for fabric. Incidentally, when we were doing the Marysprate forensic investigation, we had the critical state line, and then we went to look for evidence of high void ratios in the field. We were able to recover void ratios from block samples taken very close to the failure. In those days, it was much easier to kind of access areas like that. It would be difficult today. But the void ratios of those blocks were way above what we could reproduce in the laboratory. Even with the most careful moist tamping, the void ratios in situ were even higher in places at Marysprate. Anyway, here we've got samples prepared with moist tamping, and that were trimmed from a block sample. This is one of the sites in Australia, taken to the same starting void ratio, or very, very close. You can see the third decimal place there, but different stiffnesses, even though same void ratio. So sample A was, in this case, was taken with typical moist tamping. Sample B was started at a much lower initial void ratio. It was tamped with a lot of energy to get to that initial value of about 0.7, but then they were loaded to get to that same point. And to make sure that A and B converged, there was quite a lot of trial and error, because you need to know where to start, so you get to the same endpoint. But they had the same void ratio. So would they behave the same state parameter? Well, in fact, if you look at the loading on the right-hand side, the sample that had been prepared initially dense and then taken to that void ratio behaved differently from the sample that was initially loose. So there's kind of layers in terms of unraveling the understanding of post-peak behavior of materials above the critical state line. So I guess a couple of key points to come out of this is mechanisms 2 and 3 both generate excess pore pressures. In fact, mechanism 1 does as well, VIX mechanisms. Can be through compressive loading or shear or combination of both. Is the material dense? Is it loose? It's relative to critical state line. Looser materials generally more brittle, and the looser it is, the more brittle, very likely. And that sample preparation method matters, particularly if you're trying to capture behavior above the critical state line, in high state parameters. So, I don't know how we're doing for time, Andrew. Okay, this presentation is focusing on using CPT for trying to infer this state concept. Now, I guess we could spend an entire day really talking about this, including all the recent developments. But being day one, we try to give you an overview of what's out there and what people are doing currently. Already mentioned in the previous presentation, CPTu tests at Fundao in the sand were drained. That doesn't mean it behaved in a drained fashion. So not to confuse undrained and contractive behavior as being exclusively related. So here we got a interpretation of undrained strengths using an NKT method, but probably an incorrect NKT value. But if you applied that to one of the Fundao CPT values, you would get an interpretation that said your undrained strength ratio varied according to that orange line shown there. Okay. But if you look at the likely range from laboratory work that was done at the time, but also more recently on Fundar material by Sandra Karimi and his colleagues. The undrained strength ratio is probably about below about 0.2, 0.21 or something. So certainly way different from what you'd get if you just haphazardly applied the NKT method to the CPTs from Fundar, because they were drained as well. So just to emphasize, we can get horribly off course if you don't kind of anchor back your numbers and think, well, how rational is a undrained strength ratio of 2 in material which is actually quite loose. So in terms of what we're trying to get now with the CPT, with this cone penetration device, is are we above or below that critical state condition? And even better, how much above, if we can. But this is what we're trying to get to. Now, there are all these various techniques that have evolved, and then more recently, there's been a lot of kind of refinement of these. But Bean and Jeffries talked about this way back in the 1990s. We've heard about the PLUES method and the modified or site-specific PLUES method, where you incorporate the alpha, the compressibility of the critical state line, and then various techniques of Peter Robertson. We also have techniques using what's called the cavity expansion methods. So this was probably pioneered in the piling industry, trying to determine how to interpret CPTs and how to design deep piled foundations where they can't easily reproduce the kind of stress changes that develop during penetrating a pile. So they said, well, probably the closest analogy is to have a cavity which expands uniformly. It's like a sphere that continues to expand the same in all directions, because that's amenable to some theoretical analyses. So they kind of said, okay, well, let's start with this cavity expansion and then try and apply it to the CPT. So it's a bit of a long bow to draw, I guess. But that's where we start getting things like that widget method you heard about. So the variance then, sort of the way the sort of the family tree developed for some of these methods is the state parameter method of Bean and Jeffries, or Jeffries and Bean, whatever. I think it's a rational method. I like it because it ties laboratory testing to field testing. It seems to be based on physics more than some of the others. But you got the tip resistance method, the QTN approach, and then something called the yield stress ratio method. I'm not going to go into that in any detail. But state parameter can, at least theoretically, be measured in the laboratory and in situ in many cases. So probably spend more time on that than any of these other methods. Now, each of those approaches, laboratory methods, in situ methods, they've got their limitations quite clearly, but perhaps by kind of going backwards and forwards between them, we can improve the predictive capability and also the peak and residual strengths. Now, we talked about this earlier. We've got the corrected tip resistance, the sleeve friction, and the dynamic pore pressure, the U2. Our normalized penetration resistance, we met earlier, just using total and effective vertical stresses. We can also use mean stresses. According to that paper by Clayton, the horizontal stress, horizontal effective stress, probably has more of an impact. Because if you think about it, as you're penetrating the cone, it's those lateral stresses that are really important. Whereas with the approach on that equation shown above, on the top of that figure, it's all in terms of just vertical stresses. So mean stress would probably be more effective, more desirable. The trouble is, it's really hard to know what that is. We most often don't know what the horizontal effective stress is. Again, we could diverge in terms of what in situ methods are available, such as the self-boring pressure meter and so on. But I think I've got a slide here which just shows the variability you get with that methodology as well. So it would be desirable if we could say we use QT minus P over P dashed, but then very hard to relate that to field conditions. We can do it in the lab, but not the field. So that's what it would look like if we were able to use mean total stress and mean effective stress. But then we have to estimate K0. Now, you know, we put the slide together before seeing the work that SVA was talking about earlier. But you know, 0.5 seems to be a number that is often certainly measured in laboratory samples, but we have such changing and variable conditions in the field with drying, etc., that it may deviate slightly from that. The value of 0.7 seems to be advocated by some of the numerical modelers, but again, we don't know for sure. So in the absence of more definitive knowledge, I guess using the vertical stress is still the way to go. So this is data that we put together for that paper in Sydney in 2022. And Mike Jeffries, to his credit, processed a whole lot of data that was lying in his files at home, where they'd used self-boring pressure meters and I think some dilatometers even, to try and measure horizontal effective stress. So there's a couple of hydraulic fills, a couple of oil sands tailings, both on the beach and on the embankment. And you can see the line on the extreme right is a ratio in excess of 2. Then you've got the ratio of 2, 1, and as low as 0.2. So that's a huge scatter of results from attempts to measure this in the field. And I think that's why people have quite often kind of backed off, is saying, well, you know, it really could be just about anything. People try and do it numerically. They try and model construction of a TSF, but you have to be really cautious about that. You have to build up the fill in reasonably small increments, and it can be influenced by your choice of even the elastic stress parameters. Fortunately, we're getting more and more knowledge about K0, but I think we're a long way off using it with confidence. So to come back to then how we're going to measure this or estimate the state parameter rationally. That tip resistance is a function of a whole lot of soil properties. So and that's probably not exhaustive. So certainly be the state parameter, which is a surrogate for density. The lambda is compressibility. So your tip resistance will be influenced by that. Probably your frictional strength, your M value or your phi value, your sort of modulus of elasticity, your small strain shear stiffness, and then some measure of hardening or plastic volumetric change. So all these things are impacting on this number that we're getting from the CPT. And now we're expecting to be able to infer something from that, isolating all the other effects. So it's very much an inverse kind of boundary value problem. We know the answer, the tip resistance, but we kind of want to interrogate what the question might be. What is the state parameter? So we've got that as our desired outcome, but we've got a whole lot of unknowns that need to be taken account of in some kind of, I guess, surrogate fashion. So the issue of the range of materials with all those various parameters, the properties that affect Q is worth considering when you're using any kind of CPTu-based correlation. And I'm sure many people are using these various software packages at the moment, where you just plug everything in and then you get a whole range of plots out showing you the state parameter and liquefiable and non-liquefiable. Now that's all very well, but I think what's really lacking is an interrogation of those results. It's like looking at how rational are they? Do they make sense? It's not a bad idea to pick a few points from your CPT probe, take the tip resistance, the friction ratio, the pore pressure, and go and plot where that sits on some of these charts. Just do it by hand and see, is it actually consistent with what the software is spitting out? Because then you might have a better idea of where the phreatic surface is, so you can actually normalize maybe in a better fashion, etc., etc. So we have a range of techniques, and it's good to do that, to compare more than one. But just remember, these are all kind of empirical-based correlations to a large extent. We're not measuring state directly. Even undrained shear strength we talked about this morning, we're not measuring it directly. We're inferring it from a correlation that seems to have worked previously. So general screening to try and kind of look at material types. Louis talked a bit about that this morning, clay, salt, and sand. The approach that's, I think, widely used, and it seems to be consistent with a lot of the failure case studies I'll show you in a second, is the Robertson approach. So we've got the normalized tip resistance on the vertical, friction ratio horizontal, and remember they're both on log scales, so that always tends to kind of compact data. That dashed line shown there, the Q of 70, similar to the state parameter of negative 0.05, delineating what's perhaps dense and dilative versus loose and contractive. Not telling you too much about the state parameter itself, though. So in this case, people use things like the friction ratio as some kind of proxy for some of those parameters like friction, stiffness, and so on. So we're trying to maybe refine those correlations through this proxy being the friction ratio. So a lot of the results that have been occurred for liquefaction, where there's actually been what's called a flow failure or a true run-out type failure, have plotted below that Q of 70 value. And Class A, Class B, Class C refers to the kind of the quality of the data, because sometimes in deriving that normalized cone resistance, the only data that was available was SPTs, and then you've got to go through quite a convoluted way to relate SPT to what the equivalent cone tip resistance would be in order to use this plot. So those are not all direct, true CPT tests. But generally, it's not inconsistent with what's been observed, that value of 70. But again, Ken Bean and Mike Jeffries pioneered a lot of this work with their colleagues at the time, looking at these offshore artificial islands in the Beaufort Sea, that's off the west coast of Canada, where they're creating artificial islands to enable drilling for oil production and for exploration and so on. So they actually were depositing hydraulically into these cofferdams sand-like material to create a working platform, and they had some incidents with liquefaction that drove the interest in CPT testing and trying to find a much more perhaps rational way to interrogate CPT and come to it. So they developed, and others, these calibration chambers. So we've talked a bit about that, but I thought a couple of slides to show what these large-scale calibration chambers look like. So on the bottom right is a photo of a calibration chamber. It's about 0.6, 0.7 meters diameter, 1.2 meters high. And the idea is that you place your tailings, your sand, whatever, into that chamber at a known void ratio. So you know what the state is. Then in some of the more modern chambers, you can apply a horizontal stress and a vertical stress. So you now know what P dashed is. And you have it saturated, you can put it under back pressure, and then you drive the cone in and measure what the cone tells you. And you know what the cone should be telling you because you've set the sample up at a known state, void ratio, mean effective stress. So then you push the cone in, and if it doesn't agree, then you come up with modifications or change your theory or whatever. The trouble is that we built one at UWA, that's Juan Ayala. Louis referred to the work that Juan did. So we built a large chamber. We modified it for loose samples, because as you saturate the sample, the volume changes, it starts consolidating. With the old style chambers, you then lose contact with the loading ram because there's too much volume change. But with this method, we were able to track that volume change, keep contact, and then apply vertical and horizontal total stress and pore pressure. But the trouble is, you need tens and tens of kilograms of material. It takes maybe 2 days, if not more, to set up a sample and troubleshoot all the leaks and all the rest of it. And then the test takes 15 seconds. And then you pull out the cone and you have to take all that material out again. And maybe do you dry it and reuse it? Can you reuse the material? We think so, because you're sharing a very small volume. But it's a really painful process. And so, the people that did this work and produced the kind of data that Louis was showing you, and I've got a slide or two, it was a huge amount of work, and we owe them a debt of gratitude. What we did, realizing that this was going to take an awful long time, is we developed a mini calibration chamber at UWA, which was essentially a modified triaxial device. Again, working with our offshore foundation group, where they've manufactured mini CPTs for testing in the centrifuge. So they make cone penetration, or cones, that are 6 millimeter and 10 millimeter diameter, friction sleeve and pore pressure for the larger cone. So we were then able to do very similar tests, but in a much smaller apparatus, 150, maybe 200 mil diameter. And Juan was able to churn through probably 40 or 50 tests using this modified CPT, modified chamber. And what he did in the big one, the one on the bottom left there, is just do a couple of verification tests rather than doing the whole bunch in the big chamber. But it's not to say that I don't think we should discount this kind of apparatus, because I think where it could become really interesting, and anybody wants to do a sabbatical at UWA, just talk to me afterwards. But this effective layering, because there we could create a layered sample and actually do a cone test in the chamber. So I think that's where the future value is going to lie. Okay, so now we've got this device which you can prepare at a known state, pretty close, test it, and then see what happens, right? So this is another way of plotting what Louise plotted, where you've got state parameter on the horizontal and some normalized tip resistance on the vertical, different conditions, saturated and dry. But what sticks out to you about that particular plot? What's missing? Well, they're all negative state parameters. Not much bloody use to us, is it? So, that was what we were struggling with when we started this work, is that just about all the previous test work had been done on dense samples. It had also been done on mainly quartzite, and limited range of particle size. So valuable as it was, we were very kind of reluctant to be extrapolating that line into the positive state parameter territory. And you can see, particularly as you're getting between 0 and minus 0.1, this seems to be getting more and more scatter. So any kind of extrapolation is going to become more and more dodgy. And you could envisage putting bounds on that, which then straight away negate the value, I think. So it's very valuable, and it's good to be able to interrogate some of this data, but clearly we needed to be doing chamber calibration tests in the contractive region. And that's what Ayala did. We'll come back to that. But then that led to the expression, or relating tip resistance and state parameter through an expression such as this, where you then got two constants in inverted commas, which are a function of compressibility. And that's, I guess, where Howard Plews came to that idea of trying to find a way to estimate lambda from in situ tests, because you can't measure it directly. Remember, it's related to friction ratio. But to try and use this, we need to get lambda in order to get K and M in order to get state parameters. So lots of steps involved. The bottom left there is a figure that collates data from gold tailings in Australia and the work that George Papageorgiou did as part of his PhD, also gold tailings, berry sprayed, fines content against the slope of the critical state line. Louis had a figure up early this morning where it was a bit more of a shotgun approach. But we were looking at a specific material, and you can see the bound is fairly narrow there. So look at the layering on the top right. Does each of those layers having a different lambda, and therefore a different correlation? How thick does that layer have to be to have an influence? And there has been work on this where if it's thinner than a certain limiting value, it has very little impact on the Q value because it kind of almost doesn't see it. The cone's measuring a zonal kind of response. But still, we may need to take account of different lambda values even to apply the Plews method, depending on the fines content. Okay, so the step one when you're using that method is you correlate lambda to F with the, whether it's the Plews, the modified Plews, or some of the updated data from Dave Reed. And then people have included this B parameter, that's the change in pore pressure. Remember, I showed you earlier, normalized with respect to Q to modify that state parameter estimate. So we still have a bunch of empirical correlations. And people alternately refer to this as screening level, or some people think it's more accurate than that. Then we can use perhaps laboratory data, CPT, and cone penetration data. So this is something I put in. It's not in the original slide package, but I think what you're getting does include it. So now we've got state parameter from, again, bunch of calibration chambers on the horizontal axis. And again, you can see very few in the positive state parameter range. Q on the vertical, and the kind of pinkish zone is where we would expect loose contractive behavior. So all of those there, with a few exceptions, which were starting to creep into that contractive behavior, in particular the West Kowloon type material. But in the literature, there was very, very little available, but people were then using that data to derive these K and M parameters, right? Louis showed you this before, the scatter, that's the original. Dave Reed updated that in 2016, I think, 2015, 2016. And similarly to Louis's data this morning, there is quite a wide scatter, no doubt. However, I think if you look at individual TSFs, individual materials, that scatter is not so pronounced. So again, it's not as though it's completely random. But you do need to recognize that perhaps there is some divergence with a lot of the new tailings data plotting above that line. Okay, so let's just maybe step back with a simple illustration of what people sometimes do. So we got here silty tailings deposited underwater, i.e. subaqueously, virtually no plasticity. Loose state estimated here from the Plews method, 0.1, 0.15, maybe even 0.2, which is really high. Looking at that trace, there's a zone at about 8 meters where you're getting consistently high state parameters. You're getting higher values elsewhere, but in that region it's clustering. So perhaps it's worth targeting that zone for subsequent sampling, even more CPTs, etc., etc. So doing an initial CPT, processing the data, looking at where to target future probing and sampling is always a good idea. So in this little example, that was the target zone. I've shown you that slide before, it was from this site. So that pretty high state parameter, and yet we're able to recover samples in such a way that we could at least reasonably estimate the void ratio, and hence the state parameter for this particular material. And that then you can start like confirming perhaps the PLUS method or some of the other screening methods. If you can get in one or two places pretty good estimates of in situ void ratio, hence state parameter, and then compare with the screening methods and see if you're confident. Now, these methods of cavity expansion, as I said, they're used to kind of correlate with CPT tests, but it needs some kind of linking parameter. They've been done for both drained and undrained penetration. There's the reference for them. And you need to run this little piece of software that's been called the widget by Mike Jeffries. That's available if you get access to the Jeffries and Bean book. They give you a link and you can download and play around with this widget. So that's converting from, or you then need to convert from this cavity expansion method, which is based on laboratory measured parameters, to estimates of what the likely CPT response is. So from our chamber tests, we derived the figure on the left-hand side there. And again, this wasn't in the original set of slides, but you will have it. The one on the right was something shown by Louis, which we interrogated subsequently, where again, there's an offset between the state parameter from the widget and that from the sample. But here you can see now the two materials we tested was a gold tailings and a platinum. That's the solid lines. The upper one is blue and the bottom one is red, for those who can see red. But the two lines on the right were from the Minical tests. And here we were able to go right into the positive state parameter region of 0.1 and above. We used calibration chamber data to calibrate the widget, but in fact, it needed a change. There was an offset. You can see the two dashed lines there using the widget. So that means you then need a different K and M parameter that is very much material specific. So I guess this is an evolving technique using mini calibration chambers. Got a couple of consultants in Perth now that are building their own. So you're probably going to see a lot more of this kind of thing where you can start doing direct measurements more easily, and then maybe start using the widget with more confidence, because you can actually get much better estimates of those K and M parameters. We're seeing a lot of refinements or additions to the CPT. People using the SCPT, seismic cone. Some of the contractors can measure P-wave velocities. That's a compression wave. That can be useful for trying to detect the phreatic surface. But you can also pick up false positives if you've got a perched phreatic surface. But the seismic cone can give you a good measure of shear modulus. Trouble is you get different numbers of shear modulus from triaxial tests, using conventional displacement measurements, using bender elements, using resonant columns, etc. So I think, again, we're still not really settled on which value of G is the one to be using. But that's used then to calculate this rigidity index. So it's important we do start to nail that down. And people use that for seismic modeling and so on. Not something we're touching on in this particular workshop. So probably again ahead of time, Andrew, but anyway. Firstly, we've already touched on that. Make sure if it's undrained or drained. Using the state parameter approach rather than some of the others seems rational, to me at least. Other people might feel differently. I think it enables better utilization of laboratory data to interpret the cone, and particularly if we start including calibration chambers. But remember, it's an inverse problem. We're not measuring it directly. We're trying to get to it through a whole range of kind of subterfuge and sometimes rational interventions. And then always good idea to use multiple methods. Just see what the other methods are telling you. If there's an inconsistency, maybe interrogate why there's an inconsistency. So I think that's it. Yeah.
Okay, let's make a start. Andy's going to come back and start us off with session 4, looking at foundation characterization and classification. We specifically, in terms of structuring this course, did not spend a lot of time on foundation investigations because they in and of themselves would be a full-day course. And we wanted to focus more on the tailing side of things, but we did feel that we did need to do something on foundation soil testing. So that's the reason that this is a shorter session, and we asked Andy to try and cover that in a sort of summary way. So, Andy, back to you. Thanks.
Okay, thanks, Andrew. Nearly there, guys, nearly there. Yeah, one of the things I'm seeing quite a lot of as well, while we talked about doing this, is that often as a TSF gets bigger and bigger, and you perhaps start building a buttress, the critical surface starts transitioning into the foundation soils. So it's not all just tailings related. And I think there's been a little bit of a lack of focus sometimes on making sure we do the whole spectrum. We cover everything, because it's not just the tailings that's governing. And as we've seen from quite a few of the big failures that have occurred, the foundation soils have been pretty pivotal. So Cadia, Mount Polly, you go back to the Los Frailes in Spain, predominantly foundation type failures. So that's just something to remind people of, I guess. So I think to try and keep it narrower and to try and give a focus that I think is become evident from some of the investigations, I think this it's obvious, but it's clearly not obvious. This potential transition from over-consolidated to normally consolidated behaviour. And that was one of the key things with Mount Polly. And in the weeks that followed the Mount Polly failure, I got phone calls from quite a few companies saying, can you suggest who we can get in to do a site investigation to characterize our foundations? And I was like, what do you mean? Didn't you do it in the first place? It's like, why, just because we've had a failure, are you suddenly now awake to your foundation conditions? And I think we do this too often. Every time we've had a failure, we've then seen workshops in Perth dealing with that failure. But I mean, that's good to do that, but then you lose sight of all the other things. So that's kind of one of the key things we wanted to talk about today. And then obviously, or secondly, the mode of failure, and I'll elaborate on that. So the first one, transitioning to normally consolidated. I mean, it really is pretty straightforward. But if you look at the Mount Polly failure, it probably might not have been fully appreciated in what happened there. So let's look at a kind of very simple stress history of what might have happened. So we've got this void ratio effective stress plot again. Going back in geological time, we get accumulation of layers of sediment. It's deposited. We get this geological development of soil creeping along down that diagonal line. And we slowly but surely accumulate load. And that could be due to effects even such as glaciers, giving us a large total stress, compressing that lacustrine clay that been deposited in a lake, and over decades, maybe centuries, even longer, we've accumulated this vertical effective stress. So we're then down the bottom of that diagonal line. Then, before we talk about over-consolidation, we've got this relationship. We've talked about it enough today, I guess, already. And we assume, perhaps for clays, we've got this unique normal consolidation line. Then perhaps we get some reduction in vertical effective stress again from that peak value. And it rebounds, small void ratio change, even under quite large decreases in vertical effective stress. So if you think about what happened at Mount Polly, we had this deposition of lacustrine clay. That's that kind of, the bottom layer, I'm not sure what that color is. Then you had additional layers of transported soils being deposited, maybe a pretty large glacier. So showing that on the right-hand figure there, initial sedimentation, accumulation, glaciation, etc. Now you've got this layer at significant depth being subjected to very large vertical effective stresses, compressing to a high density. And then the glacier recedes. So we're reducing our vertical effective stress, getting that rebound line, much stiffer than the initial, obviously, but it's now in this over-consolidated condition. So it's truly over-consolidated, where, if you remember, the pre-consolidation pressure is the maximum value that it previously experienced. It's where those two lines intersect, essentially. So that's the greatest stress that layer of GLU, glacial lacustrine clay, has ever experienced in the past. Now, that's where it would have been. That's the state, the condition it would have been in when investigations were carried out. And if you go and test that material, it would probably be extremely stiff due to that over-consolidation ratio. And this is where things get deceptive. So maybe you do a test pit, 2 meters deep, and you go there with your geological pick and you push it into the side and you use the MCC SSO classification system, super stiff, this is good material. It's not going to be a problem. We don't even need to do any laboratory tests on this material because it's so stiff. Well, that stiffness could be a manifestation of the over-consolidation history of that material. So the question is, does it remain like that when reloaded? So this is taken from the forensic report. You get all these various layers, you're getting centerline, then a bit of upstream, then a downstream, then centerline. It just went through various phases. Quite a steep downstream slope was constructed. But that then reloaded that lower layer, that over-consolidated glacial lacustrine clay. And of course, it slowly crept back up that rebound line, and in places, probably not across the full footprint, but eventually it was exceeded in some locations. So now you're back onto the normal consolidation line, and your undrained strength ratio, peak undrained strength over vertical effective stress, which remember is increasing as we're building these embankments. So it's no longer stiff, it's no longer as strong as it was, it's becoming more ductile. So under that imposed shear stress, which you're getting a very significant contribution from all those embankments that have been built, you're now starting to get displacements occurring because it's more ductile, being in a normally consolidated state. So let's look at the little bit of text on the left-hand side. We've got the unloading, the reloading. The left-hand circle, that speculatively, hypothetically, that's the condition of that layer prior to the construction of the embankments. Much stiffer than it would be if it is on the normal consolidation line at that same vertical effective stress. And if you project that point upwards where it intersects the NCL, it's much stiffer than it would be at the same value of effective vertical stress. But then once we get to this transition point and go beyond, that was probably the condition of that layer at the time of the failure. And certainly, it's more likely to have been that below the highest parts of the embankment. So you might have still had some regions in the over-consolidated state, but they would have been under lower embankment heights, most likely. So now it's in a normally consolidated state. And the peak strength is perhaps about 50% of the equivalent friction, effective stress strength. And it probably got to the point where you'd got sufficient of this previously over-consolidated material transitioning into a normally consolidated state that you could then generate a potential failure surface which was similar to what you'd get in plane strain. In other words, it wasn't so localized that it was a 3D effect. So I think the forensic investigations pointed out that probably the primary issue then related to the design and the investigation. The mischaracterization of that glacial clay layer, or perhaps not even recognizing that it was present everywhere where it was present. I think it was picked up in some areas, but perhaps not fully characterized in others. But there were other things, as they always are, with all these failures that have been well documented. It's never been a single incident or a single factor, but there's probably dominant factors and secondary factors. But what was initially intended to be a temporary measure, steepening up the slope to, I think it was 1 in 1.3, which seems really very, very steep. But it probably worked because the foundation was still in an over-consolidated state, but then it became an accepted practice. This term normalization of deviance. They carried it out, it seemed to be okay, so you just kept going with the steeper slope. But now you're starting to transition to normally consolidated. But then they were clearly doing some preparation work for a buttress. So perhaps they had recognized this issue. But although that final buttress would have been great, the excavation and the work done at the toe of that facility probably made things worse as well. So there's contributing factors, I guess, were making things difficult here. Yeah, so I think the Chief Inspector of Mines used the term drifted to acceptance. I think the normalization of deviance is probably a more all-encompassing terms. But again, they were probably checking the foundation strengths based on effective stresses, not taking account of the normal consolidation and the resulting undrained strength ratio. The second point in that 2 slides back about the excavation, so that further complicated and probably contributed to the problem. They're trying to excavate down to a suitable foundation layer for placement of the buttress works. And that's not an uncommon problem, is that in order to build a buttress, you need to found it on competent material. So then what do? Do you start stripping 2 meters in front of the toe of the slope to get to the competent foundation so you can start building the buttress? But in doing so, you're kind of taking away a small buttress in effect. And we've grappled with this problem on quite a high-profile site in the last 2 years. Exactly that. How do you get to a competent foundation without kind of making the stability worse? So just in bullet points, in terms of Mount Polly, and not just Mount Polly, but I think it's a universal learning, you need to focus sufficient attention on the foundations as well. It's not just the tailings, even though that could be contractive and poor strengths, and look for evidence of over-consolidation. It's quite an easy thing to do. Just a normal high quality odometer. That's all you need. Work out where the pre-consolidation pressure is and work out what height of tailings dam is likely to give you that or exceed that pre-consolidation pressure. Now, when I was thinking about this, we've also worked on other projects in parts of Australia and adjacent countries where there's deep weathering has taken place. And you've got these saprolitic materials. So it's not like a transported soil. So if we start now applying traditional soil mechanics, we can actually often get ourselves into problems with that as well. Because it's transported soils go through the process I've just talked about. Deposition, accumulation of load, perhaps removal to give you overconsolidation, hence a pre-consolidation pressure. Residual soils, weathered in situ, have no kind of stress history in the same way. And I've had lots of arguments with people about this. If you do a odometer test on some of these residual soils, you get what appears to be a pre-consolidation pressure. But it's got, to me, it's got nothing to do with the stress history in the same way as it does for transported soils. And let me perhaps just elaborate on that a bit. So we need to distinguish, and South Africa has been very good at that. I think the kind of nexus between geotechnical engineering and engineering geology is much stronger here. Well, I hope it still is. It was when I worked here, thanks to people like Tony Brink and Jerry Jennings and so on. But you go to other countries, and there's kind of an absence of geological history understanding. I've sat in meetings and asked people, how did this layer actually ever get here, geologically speaking? Because it just doesn't make sense. And nobody can explain a geological history which explains how that layer got there. Now, it seems kind of obvious, but understanding your geology is crucially important, and I think it's been done, at least as I say, for the time I was here, it's done extremely well in South Africa. But residual soils, weathered in situ, they don't actually have an overconsolidation ratio. They have what I think we should call a yield stress. So what's the difference? Well, the thing is, it's not dependent on depth. Whereas the pre-consolidation pressure vary for different depths in an overconsolidated material because it's been subjected to different initial loading and different unloading. So your overconsolidation ratio varies with depth, but your pre-consolidation pressure likewise, but it's related to depth. We've done investigations on these saprolites where you get a complete spectrum of so-called yield stresses that are completely unrelated to depth. Rather, it's related to the depth of weathering, which in many of these geological settings can be hugely variable. So you have a weathered profile which goes up and down, deep weathering, 10 meters away, very shallow weathering. So you're going to get very different pre-consolidation pressures based on the depth of weathering. And we found in situ void ratios that are absurdly high. If you take really good quality block samples in some of these materials, you can get extremely high void ratios. I'll show you a figure in a second. Poor sampling techniques destroy that almost entirely. And then you get void ratios which kind of look more rational, but they're unrepresentative. So I think it's critically important. So this next slide is from a site in New Caledonia. That's an island to the east of Australia. It's a French territory, tropical, subtropical climate, deep weathering. And there'd been a slope failure there. We took good quality block samples, 150 millimeter diameter tube samples, conventional Shelby samples. And here you can see the differences in behavior. 4.5 void ratio is kind of inconceivable. It's like, we got them to do it again and again because I didn't believe it. But you had this inherent structure which was remnant from the weathered bedrock, and under initial loading, it was extremely stiff. But once you exceeded that yield stress, you can see that top curve, huge void ratio change. More than 1.2 void ratio change due to that yield stress being exceeded. Some of the lower samples or results were from small diameter tube samples, Shelby tubes. So you've destroyed that, that structure. You are still getting some kind of, maybe a pseudo yield stress. It's not nearly as distinct. And you probably believe that your material is a lot more competent than it is. So, yes, check for over-consolidation. If you're comfortable it's residual, transported soils. If you know you've got a residual soil profile, speak to an engineering geologist, kind of understand the geological history, and then design your sampling and testing campaign accordingly. It would be my kind of summary of that. So that's the first topic. The second is the mode of shearing. So this is, the kind of, you see this in different formats, but basically Ladd started highlighting this back in the 1980s. Below an embankment or within an embankment on a soil, maybe the kind of shearing is analogous to triaxial compression. Where the potential failure surface emerges, it's maybe similar to triaxial extension. But over a large part of that failure surface, it's probably more like pure shear or simple shear. And hence the interest in DSS testing, which is fairly recent actually, that people are using it commonly. And again, we can use Mount Polly as an example. So I took this out of the forensic report, and that sort of oval shape is highlighting part of the failure surface from numerical modeling, where the failure or the loading is predominantly simple shear type loading. So why are we applying triaxial compression data to that part of the failure surface? Maybe because it's easy. We can do triaxial test, we can impose principal effective stresses, vertical and horizontal. That little term alpha equals naught means that your principal stress direction is in the vertical direction. But even that's not what we get in situ. Those principal stresses rotate beneath an embankment as it's built. And by the time we get to simple shear, they rotated out of the vertical quite significantly. So another way of looking at it, we've got a hypothetical TSF. We've got a zone in light blue of contractive tailings below the phreatic surface. We've got partially saturated, and then maybe some lightly compacted wall raises. Top part of that failure surface, again, triaxial compression. Maybe not unreasonable to use strengths there. But for a large part of this potential failure surface, it's kind of simple shear loading, where your principal stress direction is rotated from the vertical. Shouldn't we be testing that rather? So I went back and dug out some of the early work on the simple shear test. The idea is that you apply a horizontal stress and you keep the vertical stress constant, but you allow those vertical boundaries to deform uniformly. And people tried all kinds of Heath Robinson techniques with hinges and spiral wires, etc., membranes, to try and reproduce that pure shear or simple shear type conditions. The idea is that you have no kind of complementary shear stresses, but that's hard to get away from. But these apparatuses then migrated, they developed what's called the NGI, simple shear device, Norwegian Geotechnical Institute, and now we see companies like GDS producing what's called the direct simple shear device as a commercial testing apparatus. The trouble is we don't know the principal stresses within a simple shear device. We can't get a unique Mohr circle. So it's actually, I'm very skeptical about people who derive friction angles from simple shear devices. You can get the horizontal, you can get the kind of shear strength ratio, undrained strength divided by vertical effective stress, but you can't really determine the friction angle because you don't know the principal stresses. Okay. So this is a DSS type device. You've got that base platen that can move horizontally. You see the sample there assembled with the membrane around it. It's a pretty thin sample, so it's quite convenient if you've only got a limited thickness of sample from your in situ sampling. About to be loaded with the top platen that will be applying the vertical stress. In this particular device, it's confined laterally by a stack of rings that are Teflon coated, and that they initially prevent lateral deformations, but they allow this kind of shear deformation. So a bit like trying to get that kind of distortion effect. So these Teflon rings slide over one another because they've got relatively low friction. So what you can do in this device is consolidate it under K0 conditions. That's called a zero bias test, and then you can shear it. But increasingly we're looking at as well is as you're consolidating it, you're incrementing that shear stress, because the only way you can load this test is vertically and by applying a shear stress at the interface. So you actually impose that shear stress. So when you have a test with so-called bias, it means you've consolidated under an imposed shear stress, which is probably what's happening, certainly beneath the slope. It's not the case under horizontal ground. There the K0 is probably quite adequate. So the K0 again, kind of level ground condition, we can consolidate it, sigma V dashed, and then shear it by applying these horizontal stresses. There's another illustration of that where we apply the vertical stress. We don't know what the horizontal effective stresses are. There is another apparatus that's starting to be used a bit, and I'll show you that right at the end, but we don't know those. But we then shear it from this axisymmetric condition, vertical stress in the direction of the major principal stress. And then we start moving that bottom platen. You can see how that sample is distorting and shearing. That's the no bias condition. We can also, as I said, consolidate it under an imposed shear stress before then shearing undrained. So that two kind of conditions for the direct simple shear. Illustration of the difference you get. The bottom line is K0 consolidated. There's no initial shear stress. It's then monotonically loaded in shear, as opposed to the second sample, consolidated to the same vertical effective stress, but with some shear at the same time. So it's under bias, and you can see you get more brittle behavior again. It's very similar to comparing an isotropically consolidated versus a K0 consolidated triaxial test. In this case, you're getting to the same, pretty much the same final condition, but very different peak undrained strengths. So with bias, you get a higher peak strength, but much more brittle behavior. So very briefly, we can do undrained DSS tests, but it's kind of a pseudo undrained because we can't seal the sample. A triaxial test, you put a rubber membrane around it, you put a top cap on, you put O-rings on, you isolate the sample from the cell fluid. So you can actually then prevent water flowing in or out of the sample when you do an undrained test. With a DSS, you can't do that in most apparatus. So the way we do it is we prevent the sample changing in height, which means you have to have a device, and the GDS device does this really well, that as you're shearing the sample, if it's tending to contract, decrease in volume, the vertical stress backs off. So it keeps it at the same height. If it's tending to dilate, the vertical stress increases to keep the height constant. So you're kind of doing a constant volume test, essentially. You got to have good equipment, very minimal compressibility of the loading frame, and good feedback loop. Now, that seems to be quite achievable these days with the modern DSS devices. So we're doing a test which is a constant volume, which is essentially undrained. The trouble is, how do we measure pore pressure? Well, we don't, but what you do, and there's been pretty convincing work on this, is that you say that the change in vertical stress that you need to keep the volume constant is the same as the change in pore pressure you would have had if it is truly undrained. Now that seems like a bit of a stretch, but there's a lot of convincing work that shows that that's not a bad equivalence. So we do a constant volume test, measure the change in vertical stress to keep it constant, and that is taken to be the likely or the equivalent change in pore pressure that would have happened. So hence we can do, I think quite convincingly, undrained tests in the DSS. Got a bit concerned about the small nature of the simple shear device and what are the stress conditions, because we don't know the principal stresses. So I looked into this, and people did work way back in the 1980s. So the figure on the left shows the distribution of normal stress. And you can see towards the edges, it deviates from a constant, and same with the shear stress. Over the central section of the experiment, of the sample, you're getting a pretty uniform shear stress, but towards the edge, you're getting a distinct stress gradient. And what that showed in the work that they did, because they did these sort of plexiglass type sample containers, you can get these rupture zones because of this stress non-uniformity. But the good news, which I kind of found out after doing some digging, is they found no rupture in tests done on loose sands, loose materials. So I think it's because with the denser materials, they're tending to dilate, they're pushing against the restraint, that then causes strain localization and rupture zones. A nice loose contractive material doesn't have that same effect. It doesn't dilate, it doesn't try and kind of push against the restraints. So it seems like we can get really, very likely get pretty uniform stress conditions within a DSS, which is good news. Another device that's interchangeably called the Berkeley and the UWA simple shear device. In this case, you can envelop the sample in a membrane, so you can actually impose horizontal stresses, in which case you can determine the principal stresses and potentially even perhaps back saturate the sample. But early days for that at this stage. So that's DSS for peak undrained strength. Something we sometimes may need to look at is, and now I use the term residual strength advisedly, because this is what I think is true residual strength, where you've got clay-like material or clay-like tailings, where there's a reasonably high proportion of clay-sized particles, but not just clay-sized, true clay. Because remember, you can have clay-sized particles that are rock flour. Just hard rock tailings can be very fine, but they're not actually true clays. And under large strains, that material can undergo what's called frictional softening. This is where you get particles aligning in the direction of shearing, particularly if they're more kind of platy in shape, and then the strength can keep going down. You can get eventually very low friction angles, true friction angles. You can get values as low as 8 degrees with things like very high plasticity clays, London clay, etc. So to me, that's true residual strength, as opposed to the kind of large strain strength we're talking about in cohesionless tailings. And this was, again, implicated as one of the contributing reasons to that failure in Spain in 1998, the Los Frailes failure, where it was the foundation that was the core of the failure. Now, the kind of device that's normally used here is called a ring shear device. We can't get to the strains required to mobilize this true residual strength in a triaxial or in a DSS. The only device that makes it feasible is this ring shear. And I didn't have a photograph of it, but it's essentially an annular sample. So it's like a cylindrical sample, but there's been a piece bored out of it. So it's an annular sample that's set in, similar to a conventional shear box, in two halves. You rotate the one half of the box relative to the other, but the beauty is you can just keep going around and around and around as many times as you want, if necessary, to get a stable condition where you actually have fully mobilized residual strengths. So again, if you've got a very clay-like foundation and you're concerned about large deformations because it seems to be ductile, it might be worth commissioning some ring shear tests. Okay, I think that's probably, just about it. So I think correctly characterizing foundations is sometimes been a little bit neglected or kind of put to the side. I think it's critically important, particularly as the dams get higher, because this is where the failure surface often transitions to being mainly located within the foundation. We need to distinguish between transported residual soils. For some people that's old news, but for some people clearly not. And then conducting appropriate laboratory tests to get the shear strength. And what I mean by appropriate, I mean if your failure surface is predominantly in simple shear, do simple shear type tests, because your undrained strength ratio will be lower than in triaxial compression. There's a lot of evidence to that effect. So I think that's it. Yeah. All right. Thanks, Andrew.